Hi, I'm Connor O'Brien, the science guy.
Hi, I'm Jake Fratkin.
Hi, I'm Eric Bindlingmar.
Hi, I'm Mike McGarren-Clemens.
Hi, I'm Sam Jagosinski.
And we are Group 11.
Team.
For our experiment, we chose to demonstrate the Leidenfrost Effect. The Leidenfrost Effect demonstrates the heat transfer concept of conduction. First, we will give a brief explanation of conduction. As one of the methods of heat transfer, conduction occurs when two objects in contact with each other exchange heat due to a temperature gradient. Oftentimes, our skin comes into contact with cold surfaces such as an ice cube, but have you ever stopped to ask the question,
why is my neck cold?
Good question. The temperature gradient between the cold ice cube and warm skin results in heat transfer in the system. The heat transfers from the skin to the cube, and the temperature of your skin drops.
Why can't I feel it anymore?
Another great question, Eric. This has to do with conduction in layers. You see, different materials have different conduction mass transfer coefficients, so heat will transfer at different rates depending on the material. The cloth doesn't conduct heat as well, and acts as an insulating layer between the cold ice and warm skin, so less heat is transferred. Now hopefully your curiosity is piqued by the question of how the Leidenfrost effect relates to the simple concept of heat conduction. The Leidenfrost effect is demonstrated in this pan, where it seems as if the liquid water is gliding across a surface that is much higher than the water's boiling point. But how can this happen? When the droplet comes in direct contact with the pan, the bottom layer is vaporized because the pan is above the boiling point of the water. However, the vapor layer is a poor heat conductor, and the heat that conducts through this vapor layer is not enough to vaporize all of the liquid layer. As a result, the vapor layer acts as an insulator to the remaining liquid in the droplet, which appears to float on the pan. It is also common practice in cooking to use the Leidenfrost effect to test the temperature of pans. Chefs will commonly drop water into their pans, and if the Leidenfrost effect occurs, they know the pan is hot enough. Imagine Sam is a drop of water, and the floor is a hot plate. When the temperature of the hot plate is below the Leidenfrost point, the drop of water will remain stationary and simply boil off. However, if the temperature of the hot plate is above the Leidenfrost point, the bottom layer of water will vaporize extremely quickly, resulting in a vapor cloud under the water layer. This vapor layer is represented by the air under the skateboard. Because of this vapor layer, the water droplet skids around the hot plate until the droplet eventually boils off. The water takes longer to evaporate because the vapor layer is a poor conductor of heat.
Hello friends! Today we're experimenting with the Leidenfrost effect, and what we found is as you increase the salinity of water, it decreases the amount of time in which the Leidenfrost effect occurs.
In these cups, we have an increasing amount of salinity. We have 1/8 of a teaspoon, we have 1/4 of a teaspoon, 1/2 a teaspoon, and then saturated. And what we're going to do is we're going to take a drop of each and put on the pan, and then compare how long it takes for each one to evaporate or to evaporate.
After many trials with the different salinity levels, we were able to prove our hypothesis by recording the evaporation times at different salt concentrations. This experiment has demonstrated that some materials conduct heat more effectively than others. Using these principles, chemical engineers like Mike can contribute to real-world problem solving by developing effective insulators and conductors. We hope you had as much fun as we did learning about the Leidenfrost effect and its applications to real life. Go Blue!